So let us start our solving of assignment number 3. So first problem, it is completely formula based, so there is nothing to discuss here. I request you to solve it by yourself. However, we just want to copy this formula for our reference. Just a minute, let me check whether we can uh, take some kind of. Okay, let me just try this. So this is the formula that we are going to use here for all our cases. Now I am directly going to problem number 2. So what it says, two single phase transformer each of 1000 kVA, 100 kVA having equal turns ratio. So here you are free to assume that transformers are of equal voltage rating also, and thereby whatever value for their corresponding is 1% and 4%, you can consider these are respect to same base values. So basically what how to calculate the per unit value, those who are not familiar with it, for them just very quickly let me show you that it is kilovolt base square divided by MVA base, that gives me my base impedance. So here we are assuming that KV base is same for both the transformers, and therefore 1% and 4% and 1.5% and 6% are with respect to same value. Please note the above PU values of the individual transformer were calculated with respect to their secondary side voltage at KVA. This is the irrelevant, the redundant statement rather, this one. This. Calculate the load shared by each transformer and their individual PA when the load total load is shared 120 kVA 0.8 PA leading. So one thing interesting to note that here both the transformers are having equal RX ratio. If both the transformers are having equal RX ratio, so what we can conclude that their KVA will be just like both their KVA, the total KVA will become an algebraic sum of their individual KVA. So if you have n number of transformers having equal RX ratio, then and suppose the first one is having KVA 1, second one is KVA 2, third one is KVA 3, and so on, you have KVA n. The total KVAs will become KVA 1 plus KVA 2 plus KVA 3 plus till KVA n. But these plus are valid only when you have equal XR ratio or RX ratio for all these transformers. Calculate the load shared 120 kVA 0.8 PF leading. Now coming to our here. See, please try to understand that since both the transformers are having equal turns ratio, so this part, sorry, this part become completely irrelevant. Let us discard this. So what we have these three equations. So now what I am supposed to find out, here I have to find out the two individual transformers KVA. One thing we can do is that simply we can use current division rule, find out that KVA distribution, that KVA 1 is equal to It is very easy to visualize. You see what is happening here. That it is like, suppose you have this. So 10 ampere current is flowing. Now, how much is flowing through this 2 ohm? This 2 ohm will carry how much? 6 ampere. This 3 ohm will carry 4 ampere. Right. And here in this side, you have one supply. That supply must be strong enough to support this. So the supply voltage should be, if there is no further one, how much should be the supply voltage? It must be 22 volt. Because this branch you have the drop. Now you consider how much kVA is being transferred here. So kVA transfer is how much? It is 10 volt into 10 ampere. That means it is 100. Here it is watt, since it is DC, but you can think about in analogous AC, it is kVA or VA. So 100 watt. Now how much you have got transferred out of 100? How much it is getting transferred through this 2 ohm? The answer is very simple. It is 3 by 2 plus 3 into 100. That is 60 watt. And how much of 100 watt is getting transferred through 3 ohm? That is 2 by 2 plus 3 into 100. So that is 40 watt. So 40 watt is getting transferred through your 3 ohm. Okay. Now, how much is the kind of wastage here in this 2 ohm? The wastage in the 2 ohm is how much? It is 72 watt. And how much is the wastage here in 3 ohm? It is 48 watt. So these are the amount of power wastage and the power delivered. So please note that 72 watt is the power wasted in 6 ampere, 2 ohm resistance, and how much power is getting transferred? That is 60 watt. And in 3 ohm, how much power wasted? 48 watt. And how much power is being transferred through 3 ohm? That is 40 watt. So don't get confused between these two. Uh, anyway, to coming to answer our question, what we should have here, it is 120 kVA 0.8 PF leading. So this will be getting divided in equal half. Therefore, it will sorry, not equal half, proportion to their this formula will get. It is kind of you can calculate it. So what we'll have here, KVA1 will be, you have to find out that 1% means what, say, since all these are in same base, let it be 1 plus J4 and another one is 1.5 plus J6. So you have to find out their absolute values. Since it is in Cartesian form, you got to find it in the corresponding polar form. So it will become root 17 inverse of 4 and these will become something, some values 2.25, some root 38.25 in my calculation. Tan inverse 4. So both you have this. Now you have to find out, using this formula, you have to find out KVA1, KVA2. Well, after that, what you need to do, you have to calculate the voltage regulation of this combined transformer. How can you calculate the voltage regulation? It's very simple. You have to find out this VL. So how to find out VL? The YK, you can figure it out. YK, now it is very simple. Here, this equation actually reveal how VL and VS are related to each other. So once you find out VL from this equation, you can figure out what is the relation between this. And that would give you the percentage of regulation, right? Now, what has been asked, if the share during, so this is what is being said that suppose, let me show you the analogy that I just discussed here. So what it is saying, suppose if here what is the amount of regulation when you have these two parallel branch, the amount of regulation is 12 volt, right? 12 volt drop you are getting due to this branch. And how much is the power transfer? That is 120 watt, sorry, 100 watt. 100 watt is the total power and 12 volt is the total drop. Now, what it is being asked that suppose you have one transformer, sorry, one such resistance. I'm giving you the DC analogy. You think about the corresponding AC. Here you have 2 ohm and here you have, say, the same watt, 1 ohm. So let make this 1 ohm be divided in proportion to the load, like what I am trying to tell you. Say this 1 like how, let us think about a combination of two parallel resistance that gives me 1. So say R1, R2 is equal to 1. But another interesting things or information that we should not forget, that R1 by R2 must be 2 by 3. That is coming. So R1, R2, you have R1, R2 divided by R1 plus R2 is equal to 1. And if you try to solve it with R1, R2 information, what you will have, say, if you divide whole thing by R2, R1 divided by 2 by 3 plus 1 is equal to 1. So R1 becomes your R1 becomes 5 by 3. And what about your R2? R2 will be 3 by 2 into 5 by 3, that is 5 by 2. Right. So when you have 2 ohm, you should put 5 by 3 ohm in series with that, and then we can always get, if we have this same, see, suppose you have that 22-volt source here, in here, and then how much power will be getting transferred here. Okay, forget about 22-volt, we will come to that later. But how much power will be transferred here? 5 by 3 ohm. The amount of power that we want to transfer here is 60 watt. So if you want 60 watt, what is your formula? That I square into R is 6. So what should be the I square? The I square should be, here what is your R? R is 5 by 3. So what would happen to your I square? I square will be, so that gives me some 12 into 3, that is 36. So I become 6, correct? So if 6 ampere is flowing here, then I'll have that. But then there is a, I want to realize you something. So how much power you will have? You will have, so same 2 ohm is there, say 12-volt drop is there, but how much is the voltage you are getting across this? That is 5 by 3 into 6, that means 10 volt. So same voltage here across this same voltage. Now, if you want that, accordingly, you can figure out how much current will be flowing through that 5 by 2 ohm. Your 5 by 2 ohm, it should be how much? It should be in that 4 ampere, correct? I'm not doing all this because you can figure it out by yourself, because in this case your I square R should be 40, and from that you can figure out your R is 5 by 2, so you can figure out I will come out to be 16, and that will give you, sorry, I square will become 16, and that will ensure I is equal to 4, so 4 ampere will flow, so 5 by 2, and this is again 3 ohm. So if both the transformers are sharing load proportional to their KVA rating, they are like their regulation will remain same, right? It's not that we will have any difference in their regulation. Whatever regulation they share, the proportional transformer share individual load, they will have same amount of regulation here. For your understanding, I always encourage that when solving the DC machine, sorry, transformer problem, you please think the parallel operation of transformer. You think about how parallel resistive branch converts or transfer power from one to another, and that will make your like pen much easier to visualize things. But now coming to the third one. Consider 400 kV and 800 kV transformers are in parallel. One of them has 1% and 4%, whereas the other has, please note that again, but here it is 1% and 4%, and whereas the other has So these two transformers are just like the previous case. Here they are having different value of kVA. So only difference between the second problem and the third problem is that here you need to adjust the like this per unit values. So for the first one, if you consider it is 1 and 4, for the second one, what would happen? It would become 0.5 and this would become 2. So for question number 3, you will have first transformer 1 plus K4 having base 400 kVA and say some base voltage 50 kilovolt, and the second transformer TR2, when you will convert this TR2 to 400 kVA, what will happen? See how to convert them. Let me show you. Suppose let us take one example. I have 100 VB is equal to 100 volt and KVA is equal to say, okay, make it 100 kilovolt and KVA is equal to 100 megawatt. So now what is your ZB? We have 100 into 100 divided by 100. So ZB is equal to 100. Now, if we have to convert it to another one where it is VB is equal to 100 kilovolt, same as the old one, but MVA base is now 3 megawatt. So what ZB value you will have here? Here ZB value, let this be ZB old, this be ZB new. ZB new is for this case will become so this will give me 200 ohm. If that is the case, then how things are going to change? Suppose I have in this scale, I have something as 1 plus J4. So when I will convert that same impedance in this scale, how much value it will have? It will become 2 plus J8. So similarly, transformer 2, it was when it was having 800 kVA and same VB it had 1 plus J4, but when I will convert it to 400 kVA, what would happen? This will become double. Right. So in that process, you got the value. Thereafter, what you need to do, values of the, it is just like the previous case. Determine how they will share up 600 kVA at 0.8 lagging. So the same thing, 600 kVA, you have to figure out how they will share the load. Find out the maximum load that they could be shared. Okay, this is an important part in this problem. What makes it different from the previous one? Maximum load. How can you find out maximum load? So when you have reach your maximum load, see what is the load relation. If you have this 2 plus J8 and 1 plus J4, if this is your ratio of the two uh, like kind of two transformers rating, then what you will have is 1 plus J4, they will divide the load in that ratio. And finally, what you will get, say this being one transformer is sharing X and another one is sharing Y. Now, suppose X is the amount of load being shared by 400 kVA and Y is the amount of load being shared by 800 kVA. They will share this load in proportion. So if I ask you how much maximum load they could share, then what you should do? You should first fix the, or you should assign the maximum kVA for the lower transformer with lower ability or lower kVA rating. So you assign X is equal to 400 kVA, and then you find out Y, that is Y by X into 400, and that will give you the like the second transformer or kVA transferred to 400 kVA transformer, kVA transferred to 800 kVA. And you will get some around some value 700 something you will be getting, right? Sorry, there is some kind of interruption. Just let us check the other problems. Two 800 kVA transformers of equal voltage rating are connected in parallel. One of them has 1% resistance and 4%. And so here you have first time we are encountering a problem. If we see or if we compare this problem with the problem 2 and 3, here first time we have to deal with a transformer that is having different Rx ratio, right? Because one is 1% and 4%, another one is 1% and 8% of reactive drop. So this, so find out that the maximum load that could be shared by this parallel combination of the transformer. You may for the time being you may just drop this part. Basically, this is asking how you can manage this 4%. See, when you can have maximum kVA transformation when you have equal acceleration. So basically, what it is asking for to compensate these 8% reactive drops in the second transformer and make it somewhat closer to 1 to 4%. So for the time being, you can drop this part. Huh? Let us only focus on this. So just like the previous one, here also you have to find out. But here is there is a little like catch here. What is that? See, these two transformers will share different amount of having different value of their corresponding impedance. They will share different amount of reactive power. Sorry, they will share current of different phase. What I'm trying to tell you, if I have to show it, say let us have this one transformer one transformer having one G4, another one is having one G8. So what you are having, since they are equal trans ratio and everything, you can think about them like this. But the problem here is that whatever I1 being transferred to transformer 1 and I2 being transferred to transformer 2, this current I is not going to be just simple I1 plus I2. Cannot write that. Rather, what you can have, I will become a phasor sum of I1 and I2. And clearly, in this case, I1 and I2 will not be in phase because these two are having different amount of reactance. So how we can think about what is the maximum kVA that could be transferred? So the logic says that if we go back to our previous example of resistance, what we have observed, generally the one with small value of resistance is supposed to carry the heavy amount of watt, or the like lion's share of your load uh, wattage uh, was being transferred through your uh, resistive path having lower value of resistance. So in this analogy, what we can think of that when we will consider this, the both are 800 kVA, but what would happen? This transformer having this can carry 800 kVA, this can also carry 800 kVA. But when this will carry 800 kVA, of course, the second transformer will not be able to carry 800 kVA. Why? Because the second transformer I2 will always be for equal. Please try to understand when you have connected this in this fashion. The drop across this parallel branch are same for both. Say this is transformer 1 and this is transformer 2. So drop is same for transformer 1 and 2. If this drop is same dt, dt is the same drop across transformer 1 and also dt is the same drop across transformer 2. Now transformer 1 having lower value of impedance will carry higher amount of current, and transformer 2 having higher value of impedance will carry lower value of current, and therefore the transformer 800 kVA will reach its peak capacity at first, and for that value 800 kVA you have to find out how much kVA could be transferred through your this one. So basically the formula will be you have to calculate the magnitude, that is √5 divided by, sorry, not √5, here it will be √17 divided by √65. So this is the amount of like portion will be transferred through this second transformer, right? So that you have to figure out that the amount of kVA will be transferred through your second transformer. So and then you have to figure out that if these two are in, like, say one transformer current is like this, then other transformer current will maintain some angle I1 and I2. So the resultant will give you I, right? And one thing you should not forget that when we are talking about KVA, so here you have I1 800 kVA and I2 will represent these 800 into root 17 by root 65 kVA, and their phasor sum will give you the resultant kVA, right? Here we are not interested about KVA angle or something like that, and it's not practical. But why I am associating KVA with the current? Because see, both the participating transformer as well as your load are subjected to like one common voltage. Say load terminal voltage same for both the transformer. Both the transformer voltage drop across both the transformers are same. Sending end voltage for both the transformers are same. So what we can conclude in a very like layman way or very kind of proved and informal way that KVA transferred to these two transformers will maintain same angle, just the angle between individual transformers current. KVA will also maintain that kind of angle, and that is why we are trying to, like, instead of figuring out the exact KVA thing, we are trying to find out the resultant current, and that resultant current will give me this. So basically things are very simple. What you need to find out, if this is I, say this is I, and this side you have I, this side you have I, root 17 by 65, and what is the angle between them? You have to figure out. This is the angle actually between tan inverse 8 minus tan inverse 4 is the angle between them. So if you find out this angle, and then you have to find out their resultant I. Once you get that I, whatever value I, you can always relate I with, okay, let it be say IT, and this is IT this. So you can always find out the relation between I and KIT. So if IT, here IT represent 800, so then you find out how much I you are getting, and if IT is corresponding to 800 kVA, then IT will correspond to some definite kVA value. In that way, you have to solve this problem. One current source inverter of a suitable rating mimicking an alternating current source of I ampere is feeding a single phase load through a parallel combination of two transformers. The per unit impedance values of both the transformers are equal, and they also have an equal XR ratio. Please note that this is a redundant thing. However, the KVA rating of transformer 1 is twice to the KVA rating of transformer 2. So both the transformer per unit impedance value are same and having an equal XR ratio. But what is the problem? Problem is that one transformer KVA rating is like 3 times of your second transformer. And if the load draws an current 6 kVA at a power factor angle, find out the kVA transfer through individual transformer and current flowing through them. So what you need to figure out, first you have to draw the circuit diagram. This is your circuit diagram. Now what it says, the per unit impedance. So the transformers are equal, but value of both the transformers are equal. They also have an equal XR ratio. However, values of the, like, although per unit impedance of both the transformers are equal, but since one is having a VA rating 3 times of the other, so you can understand that like transformer 1 per unit impedance is actually 1/3 of transformer 2 per unit impedance. So when you will compare them in the same KVA scale, this you will get. So basically, if this is having Z1 and this is having Z2, mod of Z1 is equal to so what we can conclude that this will carry around 3/4 of the total current and this will carry 1/4 of the total current. Now, since this is I, 3/4 I will be transferred through this, 1/4 I will become transferred through this. Since they are in having same phase, so this again will become I. Upon that, what you will have, find out the KVA transferred through individual transformer and current flowing through them. So we have already find out 3/4I and 1/4I, and then what is the KVA that we will have across our load. So load, here we have to find out how much voltage will be developed across this load. So load is having some impedance values, and voltage like the load power factor angle is not equal to the transformer power factor angle. So we have to find out this. So if I have to draw the phasor diagram, that would be make us our understanding clearer. Say this is my I. Right, that is the load current as well as source current. Now, how much is my load voltage? How I am getting this? This is theta. Now, how much is the KVA? Whatever projection will have this PL and IL, that is the total KVA. What I am supposed to find out, how much KVA is getting transferred through individual transformer. Okay, if this is the IL, then we have to find out how much is being transferred through transformer 1 and transformer 4. It is this. This is transformer 2 and this is transformer 1 current. So when you add them up, what you are getting? You are getting, they are corresponding KVA values. So if it is VLIL, so 3/4 VLIL will be transferred to this, and the other transformer will transfer 1/4 VLIL. Please try to understand how this problem is actually reducing our burden. What it says, the KVA transfer, it doesn't say that you have to figure out KVA like received by transformer 1. So KVA received by transformer 1 and transformer 2, that will make our task very difficult and different. But since it is asking us to find out the KVA transferred to individual transformers, that's very easy. Just the amount of KVA that your load is receiving, you just have to divide them in proportion to their impedance value, and you will get the answer. A single phase auto transformer is supply to power W kilowatt at unit power factor V2 volt, and the input being V1 volt, determining the KVA rating of sections of the winding. This is very simple. I'll share its solution. It's like too easy to discuss. Derive the auto transformer equation and thereafter find out the KVA conductively transfer and inductively transfer. This is just actually like I just draw something in a different manner. Actually, you have read this, so that this is in one side and I have placed it in between. So basically what you will have here, you will have say I1, and if this current is I2, then this segment is carrying I1 minus I2, and this side again it is I1. So if this is your N2, again you have that N1 I1 remains same. Whatever you had N1, sorry, N1 minus N2 I1 plus N2, that I1 minus I2, that same thing will remain here. Just the equation you have to understand properly and you have to apply it in that manner, right? So that part is just like, although it is just I placed it in this manner, but it will just follow the same equation of your what you have studied there. Nothing like no difference. Until unless I make or I play with the rods, things are remain same. Here I am assuming all this, so things are remain same, and you will get the equation in a very peaceful manner, no worries, right? Clear. So that's it.